Imagine a star containing roughly 200 times more mass than the Sun. It is not the largest star by diameter, and compared with some red supergiants, it may even appear surprisingly modest. Yet it radiates several million times more energy than the Sun and exists near the very limit of what can remain stable as a star. Its name is R136a1, and astronomers consider it the most massive known star. R136a1 is not located within the Milky Way. It lies approximately 160,000 light-years away in the Large Magellanic Cloud, a small neighboring galaxy orbiting our own. This means the light we observe today left the star when early modern humans were living on Earth. The star resides within the Tarantula Nebula, one of the most active regions of star formation in our galactic neighborhood. At its center lies R136, an extremely young and densely packed star cluster. It is filled with hot blue stars, many of which are tens or even more than 100 times as massive as the Sun. Hidden within the crowded core of this cluster is R136a1. Identifying it was not easy. From such an enormous distance, the central region of R136 appeared to be a single bright object. Astronomers therefore once considered whether it might be one unimaginably massive star. Only observations with higher resolution revealed that the bright core was actually composed of several individual stars. The most prominent among them was R136a1. Even today, we cannot observe it as precisely as nearby stars. It lies in an exceptionally crowded environment, and its light blends with the light of its neighbors. Astronomers therefore cannot simply measure its mass directly. Instead, they estimate it by comparing its observed luminosity, temperature, and spectrum with computer models describing the evolution of extremely massive stars. This is why estimates of its mass have changed over time. Earlier calculations suggested a present-day mass of approximately 265 suns and an even greater mass at birth. More detailed images, which separated its light from neighboring stars more accurately, produced lower estimates of between approximately 170 and 230 solar masses. A newer model that also calculated the physics of its atmosphere and stellar wind in detail estimated approximately 233 solar masses. The most honest description is therefore that R136a1 has roughly 200 times the mass of the Sun, although its exact mass remains uncertain. Even according to the lower estimates, it remains at the top of the list of the most massive known stars. This uncertainty is not a failure of astronomy. It demonstrates how difficult it is to determine the properties of a single point of light inside a crowded star cluster 160,000 light-years away. When we hear the words, most massive, we may also imagine the largest star. But mass and physical size are not the same thing. The radius of R136a1 is estimated to be around 40 times that of the Sun. If it were placed at the center of the solar system, its outer layers would extend approximately halfway toward the orbit of Mercury. That is enormous, but not when compared with red supergiants, whose surfaces could reach the orbits of much more distant planets. R136a1 is therefore not the record holder in diameter. What makes it exceptional is the amount of mass it contains and the energy it produces. Its estimated effective temperature is around 50,000 Kelvin, several times hotter than the surface of the Sun. At such a temperature, it radiates much of its energy as ultraviolet light, which human eyes cannot see. Its total luminosity is several million times greater than that of the Sun. In only a few seconds, it releases roughly as much energy as the Sun produces in an entire year. Together with other hot stars, R136a1 floods its surroundings with ultraviolet radiation. This radiation ionizes the gas within the Tarantula Nebula and helps produce its glowing appearance. If R136a1 replaced the Sun, Earth would not be located inside the star, but that would not make our planet safe. It would be struck by radiation millions of times more intense than it receives today. The oceans and atmosphere could not survive, and the surface would be exposed to devastating ultraviolet radiation. Because of the star's immense mass, Earth would complete one orbit at its present distance in only a few weeks instead of 1 year. R136a1 has the spectral classification WN5H. The letter W places it among the Wolf-Rayet stars, which are known for powerful stellar winds and broad emission lines. The letter N indicates prominent lines of ionized nitrogen in its spectrum. The number 5 identifies a very hot subtype, while the lowercase letter h reveals that hydrogen is still present in the star's outer layers. This is an important detail. Classical Wolf-Rayet stars are usually evolved objects that have already lost most of their hydrogen envelopes, exposing deeper layers. R136a1, however, is extremely young and is probably still burning hydrogen in its core. Its spectrum resembles that of a Wolf-Rayet star mainly because it is so luminous and its stellar wind is exceptionally dense. R136a1 does not have a solid surface. Even what we describe as the visible surface of a star is simply the layer of gas from which light can escape into space. In such an extreme star, the situation is even more complicated because the dense stellar wind creates an extended and constantly moving atmosphere. The boundary between the star and the material flowing away into space is therefore not sharply defined. This wind reaches speeds of thousands of kilometers per second. According to one recent model, R136a1 loses around 0.00002 solar masses every year. That may sound like a tiny amount, but it corresponds to several times the mass of Earth being expelled every year. Over an astronomically short period, the star can lose tens of solar masses. The cause is its own radiation. Gravity attempts to hold the material inside the star, while the enormous pressure of the radiation pushes it outward. R136a1 lies close to the limit at which these two forces begin to compete with each other. The more luminous the star becomes, the more difficult it is for it to retain its outer layers. It is so powerful that it gradually strips away its own mass throughout its life. This raises another question: how could such a star form at all? During star formation, gas must fall inward and add more mass to the growing object. But around an extremely massive young star, intense radiation and stellar winds begin pushing that material away. Astronomers once believed that stars could not significantly exceed approximately 150 solar masses. R136a1 demonstrated that this limit is not so simple. It may have formed extremely quickly in an exceptionally dense region rich in gas. The material may not have fallen inward evenly from every direction, but instead flowed through a disk while radiation escaped mainly in other directions. Another possibility is that R136a1 formed through the merger of two or more massive stars. We do not yet have enough evidence to determine which scenario is correct. If we could approach it safely, we would not see a calm blue version of the Sun. Before us would be a blinding blue-white sphere wrapped in its own rapidly flowing gas. Most of its energy would remain invisible to human eyes, but instruments sensitive to ultraviolet radiation would record an overwhelming brilliance. The surrounding space would be filled with a fast stellar wind and radiation powerful enough to tear electrons away from atoms. The sky around it would not be empty either. R136a1 lies inside a dense cluster filled with young blue stars. From a safe distance, the entire environment would resemble a dazzling stellar metropolis surrounded by the glowing gas of the Tarantula Nebula. Up close, however, it would be one of the most hostile environments imaginable. R136a1 is probably only around 1 to 2 million years old. The Sun, by comparison, is approximately 4.6 billion years old and will continue shining steadily for billions of years. Extremely massive stars consume their nuclear fuel much more rapidly. The entire life of R136a1 may last only a few million years. Its future evolution will depend mainly on how much mass it loses. It will probably continue shedding its outer layers while changing its chemical composition and spectral type. Eventually, it will run out of fuel capable of supporting its core against gravity. We cannot yet predict the exact fate of R136a1. It may produce an extraordinarily energetic supernova, but its core could also collapse directly into a black hole without a typical bright explosion. The outcome will depend on its final mass, rotation, internal mixing and the amount of material carried away by its stellar wind. R136a1 is exceptional not only because it stands at the top of the stellar mass rankings. It shows us what happens when gravity gathers so much material that the energy generated in the core begins to threaten the stability of the star itself. It is an object that lives quickly, illuminates and reshapes its surroundings with extraordinary intensity, and gradually destroys itself through its own radiation. In the heart of the distant Tarantula Nebula, R136a1 stands near the boundary of what we can still call a star. Thank you for watching, and I'll see you next time.